Okay, this is a description of what one of these presentations might look like. There's some examples created by the students already online, but this is the original germ of the idea. And I think it's the best presentations are the ones that have an interesting idea that anchors them. Something relatively simple, but not so obvious, and that asks a very straightforward question. And the simple question here is aided by this video. Which gets going here.
What did it look at? I never.
It's from the movie The Poseidon Adventure. It's a ship in the middle of the ocean, gets hit by a tsunami and gets knocked down. But the fundamental question for this mysterious fluid mechanics problem is, why do models of ships, when you look at models of ships in movies, when they used to use them in movies, look like models? How can you tell them apart? What catches your eye? First thing you notice here is that tsunamis in the middle of the ocean don't actually look like that. But here, if you look at the tsunami hitting the ship, in the middle of the ocean, tsunamis might be a few centimeters tall. Not they only when they run up onto land do they get so high. But the question is, why does that model look exactly like a model? And so that's what we'll attempt to try and understand. Okay. And so the hypotheses around it are very simple. One is that when you look at the droplets in the model and compare it with the background, they're not droplets of rain that you know, but they're meters in size. They're huge. They're big boulders of water. And so one way to examine that would be, can water actually exist as boulders of water? We don't usually see it that way. The second is that the velocities that the droplets in that movie are traveling at are actually much too fast for what they would do in reality. And so you can, in these two little boxes here, examine each of those. The first is to look at what is the maximum size of droplet you can get. You can take a droplet, you can cut it in half to two hemispheres, and you can look at the surface tension that you have to apply on the boundary of this to hold it in place. And by just balancing forces, you can show that the maximum radius that you can define for a particle is 3 times the surface tension of the fluid, density, gravity, square root. If you put the surface tension in for water, you end up with a maximum particle radius of something like 5 millimeters. And so that's potentially one of the reasons that it looks like a model, because you know intuitively, because you've never seen them, that particles of water can't be as big as they are suggested by the backdrop in that movie. The second one is just to use the idea of gravity. And so if you use a quarter scale model and you see a droplet of water traveling with that in the background, that immediately scales your eye to the velocity that particle is traveling with, that droplet is traveling with, driven by gravity. And so if it's a quarter scale model, then compared to looking at a regular background, it's moving by gravity, and you can show that the velocity at which it travels is always given by acceleration due to gravity. And so the distance traveled in any particular time is going to be the same, irrespective of where you are on the planet. And so if it appears that the distance you're traveling in, say, a quarter scale model is 4 times what your eye think it should do, then that's also a clue as to the fact it might be a model rather than something in reality. And so you can demonstrate reasonably straightforwardly that either of those ones, the fact that you can't get big droplets and that in a model the particle droplets are moving at the same rate as they would against the background of a real model. And so if it's a 10th scale model, then they seem like they're going 10 times faster than they should be, and your eye picks that up. And so those are 2 possible reasons for that. Final closing comment, is there a way to get around this? What could you do? It's not clear what you could do in terms of making the particles bigger. You need a larger surface tension. Easy to make the surface tension smaller by using surfactants, but not so easy to make them larger. And in terms of the intrinsic size, I think there's no way to get around that. So that's it. So very simple. Basic idea of an intriguing observation that's not obvious as to why it is. And that is, how your eye picks up on a model being a model rather than a real prototype. A very simple analysis to be able to demonstrate whether the hypothesis makes sense, and then some conclusion as to whether it can be or not. And that's it. Okay, thanks very much.